Hi guys, nice to meet you. I start to recognize some faces, so thank you for coming to our very regular meetups organized by Dataiku. Today I'm going to talk about translation and things like this. But before I start, who doesn't like to talk about his birthday? My company and I are in so much in love relationship that they decided to organize their first big event on my anniversary date. So please, if you don't come for the event, please come for my birthday. I'll be very happy to see you. Okay, so let's talk about the project itself. So this is the agenda for the day. I will try to make it as you. Oops, sorry, that just shut down. Yeah, is it back on? Yeah, looks like it is. Yeah, thanks. Yeah, it should be all right. I hope. So I'll. No, it doesn't work well. The microphone looks like I need to speak really closely to it. Okay, all right, should be fine. I'll explain why we decided to do that project, and then I'll talk a little bit about machine learning translation, give a bit of background, and explain how we arrived to such promising results right now, and show you a little bit of codes and demos to try to keep it as fun as possible. So the project motivation, well, as you all understand, yeah, I think it should be better with another mic. Sorry. That's fine.
I think it might be dead, maybe.
Is it better now? Yeah, oops, looks like it is. No, I think it's on the other side. Oh, yeah, there's something wrong, but somewhere else. Shall I keep going, or? Oh,
just hurry back.
Yeah, shall I just try to speak very loud? Can everybody hear me? Yeah, okay, all right, that's perfect then. So as you all guess, I'm French. Dataiku is originally a French company. And from the beginning, we wanted to be an international company. So we've got lots of people from, in the US, all over the world. But being a French company posed a kind of problem for us, especially when we're using internal chats. They will obviously not be able to understand what we're talking about. So we've got that stuff at Dataiku that we're using a lot, HipChat. And well, it's mainly run by people in France, so people in America, because we've got offices obviously in London, but also in New York, a bit in Singapore and Munich. They obviously don't understand what we're talking about. So the original purposes of that project, led from the US actually, was to be able to have a bit of fun and be able to translate what everybody would say. But it's not only that. We Dataiku, we are a data science platform. We've got lots of different customers from all over the world, Unilever being one of them. And for them, it's critical to be able to understand what people are thinking about their brands at any time. So right now, there's lots of different techniques in the world of data science to avoid translation and keep being able to understand what people are talking about. But at some point, for a company like Unilever, obviously, it's quite helpful to be able to just translate that and then read it and understand what the topic is about. So if I just say that to you, you'd be like, well, they can just, they're Unilever, they've got lots of money. They could just use the Google API, just translate everything, and then what's the big deal about building everything by yourself? The big deal about building everything by yourself is that, yeah, it looks quite okay to use the Google API, but it's an API. And the main problem with API is that, first of all, it's not free. If you want to translate it and use it quite extensively, well, you can see that Google will start to charge you $20 per million of characters. So I'm not sure how many letters there are in all the tweets that Unilever are using to make their analysis, but it's completely out of budget. And then the second big problem is that it's an API, so that means that you need to make a call, and that means that at some point I'm receiving your data. And that means that if you're sending something sensitive to be translated, well, at some point, Google might be able to see it. So it's fine if me, as an individual, I just ask for some random translation, but if, jurist company or barrister or anything like that has to translate something at some point, even if it's not that massively important, they obviously can't rely on such things. So we decided to say, okay, right, let's try what we can do, still using the Google product. Because actually most of the project was done using TensorFlow, which is the big deep learning library open source by Google, and also their sequence-to-sequence and translator model. That's also what we used quite a lot. So still, thank you, Google. So brief introduction, as I said. Building a translator is a challenging problem, especially for computers, and it's a challenging problem for computers because even for humans, it's actually quite difficult. Being in front of an audience like that, I realize that now I don't have to think in French anymore to be able to speak to you, but if I have to do this in Portuguese, I will have to think. So even for humans, it's not easy. Obviously, you understand that languages are very different. They have their own semantic, their own codes, their own structure. You can't have that very easy mapping from one language to another one. I remember that I think in German, the very important part of the information is actually at the end of the sentence, if I remember well, while for other languages, it's actually at the beginning. So if you just try to make that kind of mapping quite quickly, it wouldn't work. So you've got all those, basic dependencies that are quite complex to assimilate, even for a human. So for computers, it's even worse. But actually, when you want to build something in data science, you have at some point to rely on intuition, and especially the way humans are thinking and the way human works. And even if it's a challenging problem to translate, we don't realize how good humans are to be able to pick up those things like sarcasm, idioms, stuff that are very implicit, subtle, in the day-to-day language, and that's the basic intuition that we will use, that we will reuse when we will build that machine translation. So, for instance, if I show you that sentence, everybody understands that the word "it" here refers to the animal, even though you've got that ambiguity between the animal or the street. So, the real challenge here for a data scientist is to be able to make the computer understand that it will refer to the animal because the street can't be tired. It seems quite easy for us, again, because we're humans, but for a computer that works with only 1 and zeros, it's not easy at all. So just a bit of history, where we started in 1954 with the first translation system, and where we are right now in 2017, when everybody was amazed by the result of the Google Translate API. They thought like, oh yeah, it's translating very well. It's much more efficient than the Google Translate available on actually Google that everyone can use. People got really excited about it, and Google at some point decided to actually explain how they did it and how they solved that task. So this is here, Google Brain Team releases this paper about transformers. So before reaching the level that we managed to reach right now with deep learning, what did we used to do? We used to have this very basic model around statistics that are basically rule-based model. And rule-based model can't overcome the issue that I was talking about before. It's a very simple problem. You don't have that direct mapping from one language to another one. And there's no chance, or it seems very difficult to be able to map all the rules, all the exceptions, all the subtleties that you will have from one language to another one. So that means that even though at some point you manage to build something extremely complex that can grasp a lot of things, language still evolves during the time. So something that used to be said 20 years ago might not be the case right now, and then you need to update again and again and again. So that's not a sustainable approach. How deep learning is being able to have that flexibility that rule-based model basically don't have. It's because deep learning, the real intuition that you should understand behind deep learning is that no matter the complexity of those graphs and things like that, the real beauty behind it is that it's capturing some information and it's just translating it somewhere in a space where where it actually makes more sense, at least for the computer. That's how a deep learning network would work. So no matter the complexity and the flexibility that is needed between the two sequences that we will try to translate at some point, because neural network can just try to figure out the best possible space between those two languages, this is how you start to have that unique map between one place to another one. So a brief introduction, something that is extremely useful is the concept of hidden layer. So you need to give an input. So in our case, it will be a sentence. Then we feed that to a network, and we're going to have an outputted sentence. Deep learning has made some tremendous progress because of data, much more data that we received the past few years. But also computation increase, the fact that we're using GPUs and things like that. However, we tend to forget, and that's what I like about that approach in attention and things like that. We tend to forget that deep learning, artificial intelligence, at the end of the day, if it can be so precise and so powerful, it's because the human brain and the human intuition is also extremely good and extremely powerful. That ReLU function, for instance, everybody's using that right now, but everybody tends to forget that it's the function that replaced the sigmoid function used quite a lot back in the days, and that actually, even before GPUs, speed up quite a lot computation that neural networks were making. And that's the kind of stuff that I really like, and that's the reason why I think that human will still be able to contribute quite a lot to deep learning in academia and things like this. How to measure the accuracy in a machine learning in a translation problem? Because obviously you can't say, okay, all right, I'm going to take this sentence and see how well it's translated to that one. If I'm just taking the accuracy, so comparing word to word, it won't work. There's just not one way to translate one sentence. One sentence can be translated probably 10, 20 different ways. So you've got that metric that is called the blue score, which is, it's what it is, but right now it's actually quite good to grasp the accuracy in an unstructured problem. That formula looks awful, but what it does basically is just counting the number of n-grams that are correctly predicted altogether. So you take a sentence, you do all the n-grams of that sentence, and then you compare to the output sentence. The higher your blue score, the best you are. So this is right now the state-of-the-art approach for any NLP task. So any NLP problems, at some point you will have to do an embedding, you will have to encode something, you will have to attend, which is something quite new. When I started to learn about deep learning 2 years ago, attention was starting to be around, but first of all, I couldn't really understand it. And it's only now that we realize that it can bring so much in NLP task. And at some point, obviously, you need to predict. Neural machine translation doesn't, just follows that rule as well. You first of all need to embed, then need to encode, add a bit of attention, and then you will be able to predict an output sentence. What do we mean by embedding? Embedding is again, a fundamental concept within deep learning. It's just the ability, again, to make things that are similar in If they're similar, they should be close. If they're dissimilar, they should be very far away. A very famous deep learning paper a couple of years ago was Word to Vec. It was one of the first very famous paper on deep learning and NLP. It's the paper that basically will translate every word into a vector. And because I can put a word in a vector, then I can make those similarity between words. And I can say that if two words are close together, then they should be close in space, and if they're dissimilar, they shouldn't be close in space. The real beauty with Word to Vec is that it actually conserves the linearity. So it's a very famous example. I'm pretty sure you've heard of that before. But if you take the word vector kings, you withdrew men and you add woman, then the word vector that you will have is queen. That's the real beauty behind the Word to Vec. But that's not the only embedder that we have. Now we have Glovey and lots of other ones. So okay, you've got something embedded, right? And then how do we? What's the next step? The next step is about encoding. Encoding is when we're talking about a sentence. Obviously, it's a bit more difficult to encode a sentence because there's the concept of structure. As I said, when we're talking about German, all the information is at the end. In other languages, that's the opposite. So the order is quite important. And to tackle that task, recurrent net have been quite useful for being able to do that. So the way it works is that each word vector. I'm not going to say word vector because my English is terrible and it's difficult to pronounce. So each word is going to be inputted in the network, and then with a word, right now you're going to have an ident state, and each new word that will come in the sequence will come with the previous ident state. So essentially the network is able to understand for each new input in terms of sequence everything that has happened in the past, which is very dissimilar to what traditional multi-layer perceptron would do. Multi-layer perceptron, they just don't care about the structure. The RNN actually solved that problem. So you've got all that ident state created after the first sequence, and then the decoder we'll see later, but it's working the same way. However, there's lots of pitfalls on that method. First of all, it's very hard to train. It's very difficult to make them converge. You need lots of data. And it's very slow to train because of the recurrency, the recurrency fact. What has been quite useful in the past? One of the reasons why deep learning has been so useful the past few years is because deep learning is not new, but compared to a few years ago, we've got now the resources to make it fast. So you can make a quick experiment. If it doesn't work, you can try something else. The problem with RNN right now is that they're so complex to train and they take so long that it's difficult to make some tests and then see how they perform. LSTM is a form of RNN. It is still quite popular. It helps the training and the convergence to be much faster. And at some point, and actually this is when we're talking about, before talking about translation, with attention, we were doing it sequence to sequence using LSTM. So we've got most of it now. So we embed some words, we encode it with LSTM at some points, and then we will decode it as well with an LSTM at a later stage, and then we're able to have a sentence in English that will be later translated in French. There's a big problem with the architecture that I've just presented, is that when you feed that kind of network, obviously you cannot just feed. It's science in the end, so everything has to be structured the same way. So when I want to feed my LSTM network, I need to have my sequence to have a very specific. I need my sequence to have a very specific length. The longer my sequence, the most difficult it is to train the network. Not only because it will take huge space in memory, so that's not possible. But even if it was possible, the fact that each ident state have to compel and have to remember the state before. After the 50th sequence, well, basically there's lots of stuff that you probably lost, lots of very useful information that you've lost from lots of steps before. So that kind of approach, which is similar to a brute force approach, even though it's not. It's not very nice. It's not very elegant, and we needed to find something else. So what did we find? Well, what did we find? What did Google find? They found the attention layer. So it's a very nice paper to read. Attention is all you need. It's a bit difficult, as usual with Google papers, but when you get into it, it's actually a cool one. And plus, the really cool side is that they literally explain everything. So what do they explain? I'll try to not be too technical and make sure again that I use the right words to explain it to everyone. Attention is a type of layer, first of all. So it's a new layer that you will put in your neural net architecture. And what it does what every human being is essentially doing. When I'm talking about you right now, it's very unlikely that you remember exactly the last sentence that I've pronounced. Very unlikely. However, you know what I'm talking about. So what did your brain do? Your brain focuses on the part of the sentence that I'm pronouncing at the moment to give you an idea of what I'm talking about. Because again, if I ask you again, what sentence did I just pronounce? You don't remember. But still, you still know what I'm talking about. This is the concept of attention. So it's important for that layer to see and to put in place a good mapping, the best mapping possible between each word of my output sentence and the word from my input sentence. So I will not consider all the sentence as it was before, because there are probably some stuff that are unnecessary, and I will just focus on the stuff that are actually important for that particular task. Attention, it's useful for translation, but it can be used for anything else. And that's exactly what that matrix is showing. So for instance, when you want to translate in French, the word equipment, you don't care about weapons. Weapons from the input sentence doesn't bring any value to the translation of the word équipement in French, which literally means equipment. So as you can see here, you've got that area in white that shows you what the layer is focusing on to be able to make that mapping between an input sentence and an output sentence. It's actually a very clever way of addressing that problem and decomplexifying the stuff behind RNNs.
Can I just ask a question?
Sure.
Wouldn't you say that was context? So attention, so you're focusing on the context of, say, a concept that's being explained, or a paragraph. Isn't that another word for what you just described? Context? No?
Context, yeah, but it can also be used in another context. So it can be used there, but yeah, let's talk to it afterwards if you don't mind. A bit of math, and that's probably the worst I will do. To be able to compute that network, and because that I will not delve into the math, but the main concept behind that, if everyone can understand a VLOOKUP, that's what the network does. Again, it takes every word from the output sentence. It's doing a massive VLOOKUP to be able to understand which words are important from the input sentence. That's what it does. The softmax, in the end, it makes it attaches some weight on the input sentence, so that we are able to say for the word destruction, what is very important is destruction. The other words don't have that much weight, so they shouldn't be considered at translation time. The actual structure of the network itself looks like this. So they introduce another concept on that one, which is the multi-headed attention, which actually is helpful to understand concept. Because if I just use one set of attention, I will basically the fact with the interesting stuff with multi-head attention is that it lets you understand, it lets you have some attention, but on subspaces. And those subspaces will give you at some point some relevant context to what you're trying to translate or your content itself. A very important stuff that I almost forgot. If you look at that architecture, the real beauty here, even though it looks quite complex, is that they don't use recurrent net at all. Even for the encoding part. They're using a positional encoding to they're feeding the network with this to say to the network, well, essentially we don't really care where the position is, but remember, this is the index of each of my words, and then later on, this will be grasped at the output sequence. It's really important again because, as I said in the introduction, RNN are hard to train and they're slow to train. And having that kind of hack again is very elegant, and that's the reason why it's so powerful. Multi-headed attention. I talked about it. One last thing about attention before I show you a quick notebook. So this is how it works. Basically, you are basically encoding your sentence at first. It's very nice. It's coming from the Google word blog, and then for each new word, you're taking the hidden state, the last one, and then you're taking each new words to predict the next, plus the previous hidden state to predict the new one. Each new word, basically, you give them a new probability, and you'd be able to see them in action. So the example I'll show is that one. I'll show you quickly a brief notebook to see the difference between an RNN network and an attention layer network. So we've got that very simple task to solve. I'm going to feed my network with an input of 5 numbers, and the network is supposed to give me the first 2, and the rest is going to be padded, so we just give zeros. It's extremely easy for humans. It's a bit harder for computers, and this is what we will see right now. Okay. So this is my notebook, as I was saying. Is it quite clear? Yeah, you can't really see something, which is a bit annoying. So as I was saying, so I need to generate a sequence, so I generate my sequence. There's obviously lots of stuff to do. You can't just feed a neural network like this, so you have to make sure that it's understandable by the computer. That means at some point that you need to encode properly, so here we do one hot encoding. In here, what I did is that I created an encoder-decoder network that takes as the encoder an LSTM. So an LSTM, it's a recurrent net. And then I'm using again an LSTM to decode. And my performance, as you can see, so first of all, at training, I forgot to time it. But it took something like 5 minutes to train that one. And when we look at the result, you can see that they're not incredible. So in terms of accuracy, for that very simple task, I've got only 22% of accuracy, and it took me 5 minutes. So it's not a very impressive result. And using an attention layer this time, so this is this decoder. I took it from it's on GitHub because it doesn't come with Keras. But it's very easy to find some code to have the attention decoder. But it's the same structure, but instead of having a decoder as an LSTM, I've got an attention decoder as my output. Training is actually much faster. It took me something like 1 minute. We can see that the loss is very close to 0 now, and obviously we can also see that the accuracy is much better. In terms of training, I just train it on 5 1,000. My train set is actually ridiculously small, so that's the reason why. Well, I can get to 100%, but I just need to give it more data. So that's one of the main differences between. This shows you how one of the differences between an LSTM and an attention net. If we actually go into the paper of the Google guys, we realized that in terms of training, I was training that on my CPU, so it took a bit of time. They did the training and the experiment on a much more extensive way. What is really impressive is that the training times improved by a factor of 1,000. So when it takes you, I remember when I was the first paper I was reading around RNN, the guy was saying it took me 2 weeks or 3 weeks to train the network. Just it's basically the problem that we had in deep learning 10, 15 years ago, is that to make an experiment, it would take those guys 3 weeks to have a model and then realize that it's not good and the intuition that they have is not good. Right now, having that kind of new architecture and that kind of new layer, it significantly decreases the time you will wait to have a model, and then you can make much more experiment and things like this. The blue score itself actually increased quite a bit. Before I'm talking about the blue score, the reason why it's going so quick, I talked a bit about it before. It's because again the network itself, compared in comparison to a recurrent net, will not consider all the sequence before to make a prediction. It will just consider the very important word. So the path to prediction is actually 1, while for recurrent net it's n, the order of complexity. And then in terms of result, you can see the slight increase in terms of score. It's actually very impressive. That's just in 2 years. That's just also because we don't have that many data available yet, like properly configured. But I guess that in 10 years it will be even more impressive. And as I said, we already talked about that. The really cool thing is that now you understand exactly what the network is focusing on to make some decision. So it's not only from the input sequence to the output sequence. If we transform the problem to be an auto-encoding problem, we realize at some point that the network is now able to realize that in such a sentence, the animal didn't cross the street because it was too tired, refer to the animal. That start to give network the concept of intuition and attention, which is again very powerful. If we just change the sentence by one word, the animal didn't cross the street because it was too tired, we realize now that it not refers to the animal anymore, but to the street. So later on, when we will need to reuse that, at least the network has figured out the right space, and it understands what we human meant behind that, which is really cool. So we built the translator, fine. How did we do it? Most of it we reused everything that was available on TensorFlow. A big thanks to my colleague Alex Wolf in the US, who's done actually most of the job. And again, a big thanks to Google and the open source community, academia. It's at some point it's something that is help us to make some tremendous progress and improvement. And then how does it look like? So I can show you the notebook that we had. So the good thing with TensorFlow is that you just have to specify a couple of parameters to not only download the data, but also download some already kind of preset model. Let's put it that way. So you just have to, first of all, you need to load some parameters so that at some point you will be able to get some data from them. So they can feed your model with those data. And then here you can just change and set the parameters as you want. So in that case, for us, we decided to use Adam as an optimizer. We didn't do anything too special. And then once the model is trained, the really cool thing is that we decided to in that Haiku, we decided to make it available behind an API. So that the model, so that's our platform. So you can build some stuff in Python, whatever, and then every model that you've developed, you can make them available behind an API. So you have to provide the code to the API, not always, but on that problem, you have to, because there's some calls to make to TensorFlow, a bit of encoding. What is really important here is this part. I need to encode a sequence. Sorry, I need to translate it, and then I need to decode it, and this is what I will send back the result. This is what the result of the API would be. So once I've basically made my little package, we put that into a bot that is available on our internal chat. Sorry. What is it? Yes. And then that means that, so this is one of our bots, and at any point we can use that bot that will make the call to the API we've developed behind another server, and then that kind of code could be translate at some point. Temps de faire cette présentation, and we should have the translation. I am pleased to make this presentation. So now all of our American friends working in different geos can be able to use that stuff in the internal chat to understand what all the French people are talking about, which is a dramatic improvement in terms of productivity for the company. What's next? What would be really cool, and that's probably something in academia that they're working quite a lot, is to have not one model that should, because right now you need to have the mapping from one input language to one output language. It would be quite nice to actually just have one meta model where you could just say this is a language, this is another language, and then just give me the result. The reason why is that it's very unlikely that you will find lots of data between Korean and Portuguese. So if you just rely on the number of on the richness of the database to translate very difficult languages, you will not be able to have some very good model. So this is the reason why you need at some point to have that meta model. Hopefully we're gonna reach that one day. Yeah. That's it for me. Thank you very much, and don't forget about my birthday on the 27th of June.